Hello everybody, Root Beer here, and I'm taking a look now at question number 8 on the 2017 Euclid competition. So 8 has two parts, both of them written. A, in the diagram, line segments AC and DF are tangent to the circle at B and E. Okay, respectively. So ABC, DEF. Also, AF, connecting these points here, intersects the circle at P and R. And intersects BE at Q, as shown. If CAF is 35 degrees and DFA is 30 degrees, and FPE is 25 degrees, determine the measure of PEQ. Okay, so let's copy this diagram down. Now we're given tangents to the circle. So one of the things we could do is, we can do a better circle than that. One of the things we can do is name the center of a circle of the circle, and we know that the radii connected to the points of tangency. That's a little better. Will make right angles. So we've got to sort of use the knowledge that we've got a circle here, because if we take away the circle, we just have a bunch of lines, and who's to say that those lines will necessarily have to fall in a particular order. All right. So we'll get AB. I'm actually going to extend AB all the way up, because I think this is probably a nice way to do the question as well. They're they're common tangents, so they'll eventually intersect, unless for example BE were the diameter. So maybe this isn't the. No, this should be fine. Okay. So I'm going to have. So we'll say A is here. Goes all the way down to F. We have C down here, I guess. B, E, that goes across, intersects at Q. P is up here. R is down here. Alright, I'm going to give this a name. We'll call it T for the intersection of the tangents. Let's see, we've got 35 degrees there. It was a 30 degree here, and I think this was 25 degrees. Okay. So I could be wrong, but I think the easiest thing to do is probably just connect up those tangents. Maybe there's a way to do this with the center of a circle. So I'd put O here, and then I'd get some right angles like this. That might be a fine way to do it, and maybe I'll have to do it if this intersection of these tangents doesn't pay off. But the picture makes it seem like eventually we're going to connect up these two lines. These two tangent lines will eventually hit a point, and so then we could use some of our nice circle results. I don't think we'll need any lengths because they didn't give us any, but just things to think about. Alright, so what do we want? We want PQE. So we'll label that in green. PQE, this is the angle that we're interested in. Okay. So I think we're just going to have to sort of diagram chase here. And this angle here catches my attention because, so what I can say is angle PEF is 180 minus angle QEP minus angle QFE. So that's 180 minus 25 minus 30. So that's 150 minus, so it's going to be 125 here. And that sort of contains our green angle. And then we've got this angle up here that we can now get because it's from a whole line. So, and since I have t named, I can now say angle PET is 180 minus angle PEF. I suppose I could have named it from D, but so that's going to be 180 minus 25. That's going to be 55. 125, 55 here. Nothing else is really jumping out at me, so I'm going to call let angle PEQ equal X. So now we got this whole thing is 55 plus X. This right here is we got 25 plus X over here by the exterior angle theorem. And this right here is going to be 180 minus 25 minus X, which is going to be 145? No, 155 minus X. Okay. Well, let's note this 25 plus X at least. So angle AQB is 25 plus X. You could probably say, exterior angle. If you wanted to explain it, exterior angle to triangle PEQ. Okay, and we also know that angle TEQ is 55 plus X. I don't think that needs to be explained because we got the 55 here, we got the X here. But, since T is the common point, because we have to use some result from a circle, we haven't actually used any circle results yet. But this T here, since T is the, and I think if you dropped perpendiculars, you get a similar sort of thing. But since T is the common point of our tangent lines, we know that BT is equal to TE, and therefore angle TBQ is equal to angle TEQ, and we know that that's 55 plus X. So why does this work? I'll show you why it works on a separate piece of paper. If you needed to prove this in just a really quick minute, it's a nice circle result, but whether or not we remember all our circle results is a different story. We can prove it actually by using the center. So perhaps I should have just drawn a center instead of the point of tangency, the common point to the tangent lines. Anyway, we're going to have the same radius, and if we drop this line down here, we have a side angle side similarity. Two sides and this right angle here. Everything's going to be nice and similar. We can solve for the blue side by Pythagoras, and then we'll get side congruency. So sorry, not side angle side similarity, side angle side congruency. But the point is, you can just do Pythagoras and you get these blue lines equal, but also these two angles here are equal. These two angles here are equal. Nice little result when you have that point of tangency, and you can prove it with O. And it's all from the point of tangency here. So we're using that fact here. So now I know that this here is 55 plus X, and now I know the total's got to be 100. I can solve for X. Or sorry, not 100, 180. 180 is ABQ plus BQA plus QAB, which is 55 plus X plus 25 plus X plus the 35 that they've got there. So that's 80 plus 35, so that's 115, so 115 plus 2X. And now we'll flip over to the other side. 2X is 180 minus 115, and that's going to be 65. Yeah, we need the 5, and that would bump it to 20, plus another 60, so 65. So X is 65 over 2, which, since we're in degrees, is 32.5. And that's going to be our final answer. So anyways, that's the way I choose to do it with this point of tangency up here. I'm sure you could get a similar result just by connecting a center O, or the center O, to the points of tangency, which is usually something I recommend people try and do. There's probably a couple other ways to do this with various circle geometry results, but I think either this point intersection or the center O has got to be central in either of them. But there we go. That's 32.5. That's going to be our answer, and we've explained what we did as we went through 8A. On to 8B now, which, if I recall, is a 3D geometry problem. All right, in the diagram, ABCD and PNCD are squares. ABCD, PNCD, squares of side length 2. Okay. And PNCD is perpendicular to ABCD. So it's sort of like two adjacent faces of a cube, almost. Point M is chosen on the same side of PNC as AB. Okay. So that PMN is parallel to ABCD. So if I were to imagine this as a completed cube, M is just some point on the face opposite ABCD. I guess that's the way we think about it. And so that PMN is 90 degrees. Okay. So I'm thinking maybe I need to look at this from a top-down perspective. So with 3D geometry problems, 3D geometry can be quite hard, especially if you don't have props lying around to help you visualize things. And certainly I don't think I can get a prop exactly like this. Although if I had sort of a wooden block, I might be able to, a wooden cube, I could probably trace lines out for what M and P might be. But in the absence of actually having anything like that, three-dimensional geometry problems are hard, so we often try and reduce them to two-dimensional geometry problems by looking at them from the top down or from the side, and some combination of these two-dimensional views will usually yield useful results for us. Okay, so that's what we're thinking. So already I'm thinking top down, just because they specify that's the right angle for me. Okay, and so that PM is equal to MN, so it's an isosceles right angle. So now I know MPN is 45 degrees. And we're being asked to determine the volume of the solid ABCDPMNN. Okay. Okay. Let's draw a picture of this and maybe get some perspectives. I'm thinking front view might not be that helpful, but we'll see. So what have we got? We've got A, B, C, D, and then we go up, and then we come out a bit. But I don't think we come out all the way. I think M just sort of lies above A, B, C, D, but I don't think it's necessarily above the end point here. And then we connect everything up. So looking top view, I have sort of a square here, A, B, C, D, but P and N also lie directly above, and then M I think is somewhere here. And now we can better understand M's position above A, B, C, D. Okay, so we know these are equal, This is 2. All of these side lengths are 2. And so if we call this x, for example, we know that 2x squared is by Pythagoras. 2x squared is going to be equal to 2 squared, so x squared is going to be equal to 2. X is root 2. Okay, so we got these root 2's here. Where exactly is m, though? How far out? How far out is m? We'll call this y, because I already used x. So it splits that in half, 1, 1. That's 45, so that's going to have to be 45. So m is 1 out from Pn. But side length of 2, so it's also 1 here. So m is the midpoint. I'm sorry, not m is the midpoint. M is above the midpoint. Of A, B, C, D. So I'm starting to understand the picture a little better, and I've got some lengths going on here. Alright. So ultimately, I want to get the volume of this solid, right? That's our goal, volume of the solid. This is not a nice looking solid. I mean, I'm only just starting to understand where that point M is. So it's not the easiest thing to work out, but in general, and this goes, it's definitely true for contests, but it's also true generally in real life, I find. If there's a shape you want to find the area of, or the solid you want to find the volume of, break it down into things that you do know. Okay? So, is there a way to slice this thing and get volumes that I can compute? If I add in a whole bunch of lines, will I just sort of get a bunch of whole tetrahedra or something like that? Or if I add things to it, can I get a recognizable shape? And I think adding is going to be the way to go. As I've been saying, this sort of looks like a cube that somebody cut into. You know, I said A, B, C, D, and P, N, C, D are sort of two faces of a cube. And then I also said M would lie at some point on the face opposite A, B, C, D. So it really seems like they just sort of chopped up a cube in a weird way. So now that I'm better acquainted with what M is, I'm going to draw a complete cube. So I'll say something like, let A, B, C, D, P, N. We got to give names to these guys. We used P, M, N. You wouldn't use, so M and P. Let's call it R and S. It'd be cube of side length 2. So we'll put P here, N here. A, B, C. In the back is D. But now we got a cube of side length 2. And what we can do is we can come along and say, okay, M is the midpoint. M is the midpoint of the opposite face. And well, you don't usually have a midpoint of a face, but we'll say M is the center of PNSR. Oh, I guess the order should be reversed. PNRS. And we'll change our picture so that it's reflective of going around clockwise. Okay. So now, what is the figure that... So we'll use red to actually denote the figure that we're talking about in the problem. Okay. So, what's left over? And if I connect up here, I've split the top into 4 nice little triangles. And I sort of get one tetrahedra here, I get another tetrahedra here, and then I'm left with another shape that's sort of, it's almost like a square-based pyramid. So cube splits to our convex solid is what they called it. A, B, C, D, P, M, N. And we'll write these guys a little more distinctly. Clarity is always key when we're writing things up. So SPMA RMN C is down. Oh, no, we don't need C. We need B, which is below R. And then the other one, it goes, we've got sort of a square front here, and then everything connects up to M. So these guys are congruent, actually, by similarity. And you might want to say, they're congruent by symmetry. And then this is a square-based pyramid. M, S, R, A, B. It's skewed because the M is all on one side. So if we looked at it from another side, it'd be M, and it would be going straight up, and everything would be coming towards it from that side. But it's still square-based, so as long as we know the formula for square... Yeah, so we know the formula for the total cube. Tetrahedra aren't bad because these guys are going to be... So they're congruent right tetrahedra, in that one of the planes is perpendicular to its length. And then the square-based pyramids, these aren't that bad. So we need to compute. So let's lay out our attack plan. So A, B, C, D, P, M, N is our 2 by 2 by 2 cube minus 2 by symmetry and they're congruent triangles or congruent tetrahedra. Minus 2 copies of, we'll do the SA and P1 minus our square-based pyramid here. RSM. Okay, and I admit this question is turning out to be a bit of a perspective nightmare, and you would absolutely be forgiven for saying, well, I can't see that that's a square-based pyramid, or I can't see what the base is, and I need to figure out the height and things like that. It's a challenge. There's no two ways about it. This is, I mean, it's 8B, so it should be hard. All right, so not that hard to compute the area of the cube. Maybe we get a mark for that. Maybe we don't. I don't know. Okay, so I know SA is 2 because it's 2 by 2 cube, so it's going to be 2. And the area for a tetrahedron is 1/3 base times height. 1/3 area of the base. SPM times the height SA, which is 2. So just like a triangle is 1/2 base times height, tetrahedron is 1/3 area of base times height. If we were doing a 4-dimensional tetrahedron, it would be 1/4 volume of the base times height. Nothing that we need right now. And then it's a pyramid, so again, 1/3 base, area of the base, so area of ABRS, which isn't that bad because it's a 2 by 2 square, times the height. So I'm going to, and using the fact that M is on the side here, which I should probably point out, and we already worked out that that's 1, we'll call that point T. Times MT. This should work out for us. So now, SP SPM looks like this. It's also going to be a right angle. You get T here, and then here's N. So I know that this is 1, and each of these is root 2. M is the midpoint, so this is also going to be root 2. So PMS is 1/2 root 2 times root 2, which is just going to be 1. It's a base of 1 here. And MT is 1 from previous comments, but if you want to rederive it so all your solution is together, that's okay. But I've already explained MT is 1. I just didn't have the name T before. Alright, so let's put it all together. So 8 minus 2, 1/3 times 1 times the height of 2, minus 1/3, 2 times 2 times the height of 1. And we're going to get 8 minus 4/3, 2 times 2, minus another 4/3. Okay. So we'll make that 24/3 minus 8/3 for a total of 16/3. That's not that bad. I was expecting a square root 2 somewhere in there. But yeah, 16/3 is the area, or sorry, the volume of our weird little convex solid. And we could put a little therefore statement if we wanted to. But I think it's good. So let's go over the main beats of our theorem, or not our theorem, of our proof. So we recognized, so we did some work with M. Honestly, the top view stuff could probably be moved to later, and there's probably a way to do this with a side view. I think, actually, if we were to chop, I think you could chop it into other pieces, sort of a wedge, and then another square-based pyramid will work too, and then in which case you'd sort of need to do a side view for M up here. Yeah, so that'd be another way to do it, and I'm not going to do it now because this video is probably long enough, but that'd be another way to do it, and we could confirm that it's probably going to be 16/3 for our answer. But we needed a perspective to get some more information about M. We did find out that M is the midpoint of the opposite face, and that got us thinking, okay, it's really just a cube, remove some things. I think the hard part of this question was understanding what we removed from the cube to get our solid. So in that regard, maybe it was easier just to, instead of saying it's a cube taking away things, really hard to sort of visualize on 2D paper, might have been easier just to say, okay, it's the wedge plus the square base, or not square base, but rectangular based pyramid there. So maybe that's the easy way to do it. But so we did cube, remove some stuff. I think we're looking back on it now, made the question a little hard on ourselves, but I didn't see the wedge. That's my goof. So we split it up. We said, okay, these two are symmetric, so we only need to compute one of them. And so cube, not that hard to compute. Tetrahedra, as soon as we figured out the area of the base, not that hard. Square base pyramid, we got lucky that M, S, and R were sort of in the same plane, so that made that height really easy to work out. But other than that, we just sort of needed a formula for tetrahedra, and you'll notice that it's the same sort of thing for tetrahedra, square base pyramids, cones, 1/3 base times height. That's in general how it works. Anything that tapers to a point from a fixed flat area all has this same sort of formula, which is something that some calculus courses even bother to show. But that's really it for us. It was cube minus those two solids, and that was the difficulty. And obviously, as I've noted, we could have done wedge plus the square-based pyramid, and there's probably other ways we could have divided this whole thing up. So lots of plans of attack. It all depended on what was best for your perspective. By the way, let me know in the comments if you what did you do? Did you take a cube and chop things away from it, or were you smart enough to realize it's a wedge plus a square-based or rectangular-based pyramid, or did you have another way of doing it? Maybe chop it down the middle and do something. I have no idea. But either way, 16/3 is the answer here, and I'm just really curious to see what other ways people divided this thing up. Anyway, moving on, we'll do question number 9 in the next video, so we're getting close to the end here. I will see you for question number 9 on the 2017 Euclid in the next video.